Okay. Now, before continuing, let's get back to the previous exercise. So, if you already have the files, you can get them back. Because I wanna, before continuing, I wanna make an experience for calibrating, trying to calibrate the model that we set up last week, and therefore I need to introduce you to some additional R features that we will use them later on. And just 1 second, because I am installing R and it's almost finished. Basically, in order, I think you don't need any suggestion in order to get back the previous files. If you restart R and you saved, of course, the past week's work, if you just start R from where you worked last week, it should be fine. And I need myself indeed to, anyway, I need myself to get the data back. I think, okay. Good. I am just getting the data back for me. Okay, here I am. Installation should be finished. So, okay, good. Okay, I am reloading the data now. I am quickly reloading the data, quickly remaking what I did last week. If you have any question on this, just let me know. Buongiorno. Okay, so. You also need the river flow data because in order to calibrate the model, we need to compare the simulated data that we get with the observed one. So you need to get in a column also the river flow data. And just let me make a check, I want to be sure, okay. So I have now rainfall and evapotranspiration, I copied them back. And I'm not sure, I think you already have the river flow data, but in any case, if you don't have them, I just would like to remind you that you find them in my web page. So if I go back to my web page, there is here river flow data, hourly data for 1 year. And therefore, I am now uploading them. The file is called portate.tape.txt. And if I will remember, there is 1 line to skip. Just let me make a check. 2 lines to skip. So I go back to R and then I can write portate equal scan, file name, and then comma skip equal to, and that's it. Okay, now the only thing that I need is the model. Let me see if I save it in Okay, this is the model that we wrote. So I am just copying it back to R to simulate, and then okay, it was just 1 second. I changed the name of the file with the rainfall. One second. C was 0.5, if I well remember. And then I can copy this. Okay. Now let me see plot Q. Oh, okay, let me make a line. Okay, this was our simulated hydrograph. And then let me, just to get back to the previous situation, let me plot over it the observed data. So, I can write lines, portate, col, equal, red. Let's see. Okay, this is the previous situation where we got. And sorry I took some time because I had the new PC. So basically, at this stage, I changed the runoff coefficient and I put it to 0.3. This was the last thing that we did last week because I noticed that the simulated flow, which is which is black, is too high with respect to the red one, which is observed. And then I tried to adopt a smaller value for C, because C is just a multiplying factor. The runoff coefficient is just a multiplying factor. So if you reduce C 20%, you get every observation of river flow that is reduced by 20%, of course the simulated ones. I'm not sure if I start the camera, sorry, 1 second. Yeah, it was. So basically, now the question is, can we determine the best value of C in an automatic way? Because what I did last time, it was a kind of trial and error. So is it possible, again the question is it possible to find the best value of C in an automatic way? And of course the reply is yes, but we have to learn how to do that. And first of all, if you look at this hydrograph, let me make a preliminary consideration. If you look at this graph, you may see, and we already noticed that there is a big difference in fit in the first part of the hydrograph with respect to the second part, because the first part is slightly underestimated. You see that the red line is slightly lower than the black line, so you have a slight underestimation. The second part, you have a very strong underestimation. So you have a different behavior of the model in the first part with respect to the second part. And you know, this is a bit of a problem, which happens frequently in hydrology, which means that you have a different goodness of fit in different parts of the hydrographs, and therefore you have to make a choice. you have to decide whether you want to get a good estimation in the first part or in the second part. First of all, what could be the reason for this? There might be several reasons. First, it could be that indeed once that the parameters are wrong, once that their value is not correct, and it can't be correct at this stage because we just tried, we just make a couple of attempts. So it could be that indeed we can improve them. So once that the parameters are not correct, it may happen that the model looks not well performing in some part of the hydrographs, but it could be just the reason that the parameter is not correct. And I try to better explain. If you have a parameter, for instance, that is acting in a different way on the high flow and low flows, for instance, some parameters are effective on the high flows and they are not effective on the low flows. Which means that if you change the parameter, you obtain a change in the high flow, but not in the low flow. So you may get the feeling that the model is good for the high flow and not for the low flow, and vice versa, and you may think that the model is not correct then. Instead, it's only a matter of finding the best value for the parameter. So this is the first question that you should ask yourself. When you see a situation like this, the first question is, if I try to optimize the parameters, can I reach a better agreement? So the reason could be just the parameter value that is not correct. And I remind you, we are not investigating the fact that the model is not good in the whole hydrograph. We are now investigating the fact that the model is not good in just a part of it, like you see here. So the first reason could be, as I said, wrong parameter value. And then you have to elaborate a preliminary perception. Could this be the reason in this case for this, let's say, inconsistency? The reply is of course not, because we have only one parameter here, and this parameter is the runoff coefficient. If you change it, you change the shape of the hydrograph over the whole hydrograph, just according to a linear reduction. So if I reduce 20% this runoff coefficient, I get a reduction of 20% over the whole hydrograph. So it's clear that in this case, it's not just a matter of a wrong parameter value, it's something more. This preliminary perception is extremely important. When you apply a model, you should elaborate in your mind a preliminary picture of what you are expecting, of what kind of results you could get. This is extremely important because, you know, it's extremely important when you see that something is wrong, that you get a preliminary perception of what the reason could be for that. And you just don't move by trials and error without understanding anything of what's going on. You need to try to get a perception of what's going on when you apply mathematical model. This is, as I said, extremely important. And if you have knowledge of the theory underlying the model, this is much helpful. Because in this case, for instance, you know what changing the runoff coefficient induces in terms of the results. And you know that because you know the model that you are applying. And again, the knowledge of the underlying theory is extremely important. And this is why I always suggest students not to blindly apply models. If you apply a model, even if it is a commercial model, a commercial software, you should get an idea of the underlying theory. Because otherwise you can't really apply the model in an expert way. You just blindly apply it, but you know, if you are a professional engineer, you take a responsibility for what you're doing. And you can't just get an excuse by saying, look, it was the model that was wrong. No, in any case, when you sign or design a project, you sign and you take the responsibility. And in order to understand if what you are doing is correct, when you use a PC, when you use a model, you have to know the theory. So this is why I always tell students, please be very careful in applying models without knowing anything about the model itself. So in this case, to make it short, our knowledge of the theory suggests us that it's not just a problem of changing C. So the problem is something else. And in this case, what could be the reasons for this inconsistency? Another reason could be, given that I see that the inconsistency is at the beginning of the hydrograph, a second reason would be that any model needs a so-called warm-up period before getting into full operation. The warm-up period is necessary because if you have state variables in the model, they need to get to a situation where they are warmed up, meaning, let me make an example which is simpler. If you adopt a linear reservoir model, you start with the reservoir which is empty, and this is not a reasonable situation because in nature, when something happens, it happens on a catchment that is not empty. It has some water stored in it. But you start with an initial condition which is not correct. And therefore, the effect of this initial condition, in any differential equation, you know that the effect of the initial condition when you integrate the differential equation tends to vanish after some time. So you need a certain time, if you started with a wrong initial condition, to get the effect of that initial condition vanished. And this is a warm-up period. So you need a warm-up period for the case of the linear reservoir to get to a situation where the water content in the catchment assumes a reasonable value. So this could be another reason, but again, here we are talking of a model, we know it. What is this model? It's just computing the river flow by considering the past 15 rainfall data. After 15 time step, you don't have any more effect of the past. So the warm-up period for this model doesn't exist because it's just 15 hours, 15 time step. Here we have an inconsistency that is lasting for about 1600 data points. So it could be, in this case, it can't be a problem of warming the model up. Okay. But keep in mind that if you have a more complicated model like Hydrology, it takes some time to warm up. And the some time could be a couple of months. Let's say 100, 200 time steps, or even more. Do you have a question?
I didn't understand why the warm-up period doesn't apply in this case.
In this case, basically, you don't have any state variable here. It's just computed the river flow. This is a time area model by taking a linear combination of the past 15 rainfall data, which means that the river flow is just expressed by taking into account 15 past data. So when you start with your simulation, if you start from time 16, as we did, you already have the model that is warmed up because you don't have any state variable. I hope this is clear, meaning that, you know, in the linear reservoir instead, you have the water storage W, which needs to get to a stable value. In this case, you don't have any state variable. So it's just a linear combination. The linear combination, the linear regression, it has, in this case, it has a warm-up period that is just 15 hours. If you think of the linear reservoir instead, in principle you have an effect of the past that is extended to the whole future, because the linear combination is extended for an infinite number of past rainfall data. Of course, when you get very far from the current time in the past, the effect vanishes, because if you think of the, I want to be clear, if you think of the H instantaneous unit hydrograph of the linear reservoir, this is expressed by this relationship. You have it in your notes. Instead, for the time area method, HT is equal to 1 by A day over dt. You have in note these expressions for the IUH of linear reservoir and time area. And what are these functions? Representing the EUH. Basically, here, using these functions, you find the coefficient of the linear combination. The linear combination of past input that gives to you the river flow. If you look back at my expression, which was ut is equal to the integral between 0 and t of p tau h t minus tau in the tau. What you see from this relationship here, you see that the h are the coefficient of the linear combination of the past rainfall data. And so these are the coefficients. Now, you see that the derivative of the time area curve takes values only in the time span comprised between 0 and concentration time. After the concentration time, these coefficients are 0. So the warm-up period is just the concentration time, in our case 15 hours. Conversely, if you look at the first one gives to you an infinite number of linear regression coefficients. Of course, they tend to 0 for increasing t, but the warm-up period is much longer. I'm not sure I was clear with this, because you have to have clear all the previous theory, which probably you didn't have time to study so far. But if you have cleared the previous theory, you can understand that the warm-up period of let's say, the effect of the past in the time area method is just extended to the concentration time. Because if you look at the EUH, you see that it's 15 hours long in our case. For the linear reservoir, the EUH is much longer. Again, I'm not sure it is clear at the present stage. It takes time to get these concepts, but it's important for the reason that I mentioned, because you get a perception of what you are expecting from the results. Other questions on this? Don't be concerned. If it's not clear, let's discuss. Okay, so what could be another reason for this inconsistency? Another reason could be that the model is not correct, and being not correct, you may realize that it's not correct only for some parts of the hydrographs. So one further attempt that we could make is to change the model, but we don't want to do that now. Okay, another reason could be that the data are wrong. Sometimes it happens that you get observation errors, and the observation errors are limited to a part of your observation period. And if the data are wrong, there is nothing that you can do. Or there is one thing that you can do, is to reject this data. And this is what we do now. Given that it's clear that we can't change the model because we don't want it. Given that it's clear that it's not a problem of warm-up period, then the only choice that we have in this case is, the only reasonable choice is either to keep the hydrograph as is, and we give up in reaching a good simulation, we will reach a compromise, or the second solution is to remove the first part of the hydrograph where we see that the fit is not good. So in this case, we could start from time 2000. It's better if we start from let's say here it's about 1000. I think we can start from here, which is okay. Let's see. Now from here, let's start from 1800. Okay. So if you want to start from 1800, the best thing is to remove completely, because for a reason of practicality, let's remove from our time series the first 1800 of data, just for practicality. And then if we want them back, we can rescan the input file. So let me go back to R, to the R console. My time series are called pioggia, portate, and evapo. So let me reduce them. So pioggia is equal to pioggia from 1801 double dot. Okay, it wants also the second here. This is the instruction that I use to reduce the length of the vector pioggia. And then let me do that with the evapotranspiration. And then let me do that with portate. Okay. Now, just to see if everything is correct, let me redraw the plot. And to redraw the plot, I go back with the upper arrow. It's here. Plot. Okay, Q. The problem I have to reduce also Q. Sorry, Q. Because portate is observed, Q is simulated. Okay? Now I reduced everything, let me redraw the plot. Here, and then I put the lines, and then I move back to the plot, which is here. Okay, we remove the first part. Now we see that the fit seems to be reasonable over the whole hydrograph, and let me make some trials reducing the runoff coefficient. Okay, so in order to do that, increasing the runoff coefficient, sorry, because I have to reduce the simulated river flow. In order to do that, I have to write like C equal 0.2. And then I need to know what is the length of the series that I obtained by removing the first part. The length is 6960, and I need to know this length because I have to modify the code for making the simulation. So the code here, I have to change 8760 with 6960. Okay, at this stage I can go back. Here. I remade the simulation. Now let's see how the graph behaves. Let me redraw it. And here we are. A bit better. Probably we can reduce even more. But now, there is another thing that we could make to change the time area curve, but let's not do that for now. Now the question is, what is the best value of C that we can obtain? And the question is, let's find it in an automatic way. Okay, so first of all, if we want to make an automatic calibration of C, we need to define an objective function. I mentioned to you already that there are several different objective functions that we may use. Let's use, for now, least squares. square is the sum of the squared errors. Let's use this. Okay, then, in order to compute the least squares, we need to do that. Pay attention. We need, for any possible trial value of C, we need to run the model, compute the error, square them, and take the sum of the squares for any possible value of C. So basically, what I need to do is these steps: fix C, to run the model, three, compute the errors, four, square them, five, compute the sum of squares. This is what we have to do. And this is not done manually. It's to be done by the PC. But first of all, what we need to do is to write a code that makes these 5 steps in sequence. And so far we don't have this code. We have just a code so far that runs the model. This is what we have. Okay, so at this stage, let's modify our code. Let's extend it to make these 5 steps in sequence. Let's skip the first one because, you know, the first one is to be done by the PC, fix the C value. Or if we want to do it manually, we can do it manually. Let's skip the first one because, of course, the C selection is something that is not automatic. This is the starting information. We need to provide it to the PC or tell the PC to elaborate it himself. So it's not an automatic selection that we can put in a code. But once that C is defined, everything else is automatic, can stay in the code. So let me go back to the code then. The code is this one. Let me see if I can increase the font. Yeah. Control plus should be perfect. Okay, first of all, let me go back to the previous situation because I don't want I want to keep everything. So I'm going to copy this here and I'm going to work here now. I want to keep a copy of what we did last time. So 6960 was, I think. 6960. Okay. Okay, here we are. So basically, let me put some asterisks here. This runs the codes, runs the model. Now we have to compute the errors. So the errors are the difference between Q and portate. So the errors are, let's call it R, is equal to Q minus portate. It doesn't matter the order in which we take the difference. Q minus portate is the same for us than portate minus Q, because we have to square it afterwards.
But we fixed also C in this model, so what is the...
C is to be fixed before running this. And I said that I can't include the assignment of the C value in the code because this is the basic information that we can't include in the code because it has to be selected by either ourselves or the PC. We can't put it in the code because what the PC does or ourselves do, we basically select a C value ask for the PC and then run the code. If we run the code and the C value is overwritten, there is, it's not correct, okay? So we have to skip it. Okay, now let me square the error. So R is equal to R to the power of 2. Of course, I can condense these instructions in just one and just writing the code explicitly at each step for the sake of clarity. And then let me take R squared is equal to sum R. Okay. Now let's try this code. Now we have, sorry, in order to try it, I copy and paste it. Now we have the C value, I don't remember what it is. Let's start again from 0.5. And then I run the code. And then let's see, R squared is this value. So let's keep it in mind. And let's see if we take C0.1, if it is reduced. I run again. It's indeed reduced.